Welcome to the deep dive, where we really try to extract the crucial insights from some pretty complex topics.
Glad to be here.
Today, we're tackling the world of lean systems. You know, that powerful management philosophy focused on slashing waste and, well, maximizing customer value.
Right. And it's got its roots, famously, in the Toyota production system, a real shift in thinking.
Exactly. It's more than just tools, isn't it? It's a whole approach.
It absolutely is. And for this deep dive, we're not just, skimming the surface. We want to focus on two key methodologies that really bring those lean principles to life.
Okay, which ones are we diving into?
We'll be looking closely at cellular manufacturing, sometimes called one-piece flow production systems, and also the very well-known quality improvement framework, Six Sigma.
Ah, Six Sigma. Okay. So we've done the prep, gone through the materials. Our aim today is to give you, the listener, a really clear picture of how these actually work.
Yeah, what are the core ideas? What steps are involved if you wanted to implement them?
And we'll also look at the real world benefits, but also maybe some of the potential challenges or limitations.
Right, arming you with some practical knowledge for boosting efficiency and quality.
Okay, sounds like a plan. So let's dive in. First up, cellular manufacturing and one-piece flow. The sources say this is a kind of subsection of JIT and Lean connected to group technology. What's the basic idea?
Well, at its core, it's really about three things: speed, variety, and waste reduction.
Speed, variety, waste reduction. Okay.
Think about moving products through the system as fast as possible, being able to make different but sort of similar products efficiently, and just cutting out anything that doesn't add value.
Okay, so I'm picturing a traditional factory, maybe different departments doing different things. How does a cellular setup actually look different?
It's quite different. Imagine multiple self-contained units or cells right there on the assembly line.
Okay.
Each cell has all the equipment it needs to do a specific set of tasks. The product then just moves step by step from one cell to the next.
Yeah.
Exactly, until it's finished.
Yeah.
And a very common layout you'll see is U-shaped.
U-shaped. Why is that?
Well, it actually makes supervision much easier.
Yeah.
Because everything's closer together, more centralized. One person can often oversee the whole cell's operation more effectively.
Ah, interesting. Okay. The documents also mention a big advantage being operational flexibility, helped by automated machines. How does that play out in practice?
Yeah, that's a key point. The automation within these cells, it gives you much greater agility.
Yeah.
So if you need to ramp up production of one specific model or maybe introduce a slightly tweaked version,
Right.
the automated nature of the cells just makes those adjustments much faster and more precise than in a traditional setup. Even rolling out design changes becomes smoother.
Makes sense. So how do you actually create one of these cells? I'm guessing it's more involved than just moving some machines around.
Oh, absolutely. It starts with identifying all the steps needed for a specific output that could be a part, or maybe even just a set of instructions. Then, the goal is to consolidate those processes and, crucially, get rid of any extra unnecessary steps.
Right. Cutting the waste.
Exactly. And a big benefit here is communication and problem solving. Because everything for that output is in one place, problems get spotted faster, people in the cell can talk and fix things quickly.
And the payoff.
It can be pretty significant. We're talking gains in productivity, improvements in quality, and at the same time, reductions in inventory, the amount of floor space you need, and lead time, how long it takes to make something.
Wow.
Which is why, sometimes you hear it called the ultimate in lean production.
The ultimate in lean production. That's quite a claim.
So if someone listening is thinking about this for their own work, what are the basic implementation steps?
Okay, well, the first phase is usually grouping parts into families.
Families.
Yeah, based on similarities, either how they're designed or the manufacturing steps they need.
Got it.
After that, you need a pretty detailed analysis of each family. This can be time-consuming, but it's really crucial.
What kind of analysis? For manufacturing families, it often involves something called production flow analysis, or PFA. For design families, it's more about digging into the product data itself.
Okay, so you group the parts, you analyze the families, then what?
Then the logical next step is to actually create a dedicated cell for each part family.
Right. Sets up the mini factory?
Pretty much. And interestingly, there are actually mathematical models and algorithms that can help plan these out.
Really?
Yeah, they can factor in things like plant locations, market allocations, the mix of parts you're making,
Yeah.
all trying to optimize and minimize costs.
You mentioned production flow analysis, PFA. Can you elaborate a bit on that? Why is it so important here?
Sure, think of PFA as a way to systematically identify items that are made using the same or very similar sequences of processes and equipment.
Okay.
The idea is if you group these parts into families and then group the equipment they share into cells, you drastically cut down on how much you need to move materials around.
Less movement, less waste. Back to the core principles.
Exactly. So that machine part grouping is really central to making cellular manufacturing work well.
And the sources mention something called the rank order clustering algorithm. Sounds a bit intimidating.
It sounds more complex than it often is in practice. It's
Okay.
actually a fairly, well, straightforward method for doing that machine part grouping we just talked about.
How does it work, basically?
It's a step-by-step process. You create a sort of grid, a matrix, showing which machines work on which parts. Then you assign some numerical values, binary weights, and rearrange the rows and columns based on those values, iteratively.
And that reveals.
It helps reveal the natural clusters, groups of machines that tend to work on the same groups of parts. It just provides a structured way to see those connections.
Okay. So PFA and algorithms like that help figure out what goes where. Are there different ways to actually form the cells based on that analysis?
Yes, the materials point to three main strategies, essentially.
Or?
First, there's part family grouping. You figure out the families first, then bring the needed machines together. Second is machine grouping. You look at parts that follow similar paths through the factory, group the machines based on those paths, and then assign parts to those machine cells.
Right.
And the third is machine part grouping, which tries to do both simultaneously identify the families and the machine cells together, more integrated.
Gotcha. Now, thinking about the actual workflow day to day, how does working in one of these cellular setups feel different compared to, say, a traditional assembly line or a process layout where all the drills are in one area, all the lathes in another?
Oh, the difference can be quite noticeable. In a cellular flow, you generally see a much smoother, more linear flow of materials. Less backtracking, less waiting,
More efficient movement.
definitely. You often get better machine utilization too, and you tend to use your floor space more effectively.
Mm-hmm.
Productivity usually goes up compared to a process layout.
Any other differences?
Yeah, you might see more standardization of components, which helps. And perhaps surprisingly, employee morale can improve. Maybe because teams feel more ownership. Quality control also tends to be easier to manage within a cell.
And operationally, things like planning, paperwork.
Big impacts there too. Usually less planning effort needed, less paperwork floating around. Setup times can be faster, less downtime. You see less work in progress inventory sitting around, lower material handling costs, and potentially lower labor costs, both direct and indirect.
That's quite a list of potential benefits. It sounds almost too good to be true. Surely there have to be some hurdles or challenges when you try to implement this.
You're absolutely right to ask. It's not always simple. There are definitely difficulties.
Like what?
Well, you might have exceptional elements, parts, or processes that just don't fit neatly into any cell. The physical distances between machines, even within a cell, can matter.
Logistic.
Right. And identifying and dealing with bottleneck machines or bottleneck parts is always critical. Deciding where to put machines or moving them if needed can be complex and costly.
Okay.
Sometimes the routing for certain parts isn't straightforward. You can get variations in how busy different cells are. Figuring out the best way to transfer materials, both inside a cell and between cells, takes thought.
And what about changes?
That's another big one. Reconfiguring cells if your product mix or demand changes. That can be a challenge. Dealing with fluctuating demand, managing operation times. It all requires careful management.
So, okay, acknowledging those hurdles, let's just quickly recap the main advantages again. What are the big wins?
The big ones are definitely reduced flow time, things get made faster, and reduced travel distance for materials, big efficiency gains there.
Okay.
Then you typically see better use of floor space, less work in progress inventory, tying up capital, less cost and effort in material handling, and simpler scheduling.
And quality.
Yeah, usually less scrap and rework because problems get caught quicker within the cell. Costing can become simpler. Production and quality controls are easier to manage. You can isolate underperforming cells more easily too.
Anything else?
On the people side, you often see better group cohesion, maybe more worker motivation, and potentially lower overhead costs over time.
But you flagged one potential downside earlier, something about flexibility.
Precisely. That's the main trade-off to be aware of. Because cells are often designed and optimized for a specific volume and mix of products.
Right.
If customer demand shifts significantly, or you need a completely different product range, reconfiguring those specialized cells can be expensive and take time. It can be less flexible than a traditional layout in that sense.
Okay, that makes sense. Potential limitation to weigh. Let's shift gears now to our second major topic, Six Sigma. This is a term I think many people have heard. What is it, in essence?
Six Sigma, fundamentally, is a quality improvement technique, a methodology. Its main goal is to find and eliminate the causes of defects or errors in business processes, particularly those that affect customer satisfaction.
Okay.
It started famously at Motorola and then really got popularized by GE under Jack Welch. It uses a blend of quality management methods, statistical analysis, and a special infrastructure of people within the company, like black belts and green belts.
So the ultimate goal is getting super close to zero defects, right?
That's the aspiration, yes. The core idea is that if you can measure how many defects you have in a process, you can systematically figure out how to eliminate them.
Data-driven.
Very data-driven. And the sources mentioned you can use it alongside things like a balanced scorecard for an even more rigorous way to measure performance.
And it rests on some basic beliefs or assertions, doesn't it? What are those foundational ideas?
Yes, there are a few key ones. First, it really pushes for continuous efforts to make processes stable, predictable, and crucially low in variation. Variation is seen as the enemy. Second, it holds that pretty much any process can be measured, analyzed, improved, and then controlled. MAIC, we'll get to that.
Right.
And third, maybe most importantly, it stresses that achieving real, sustained quality improvement needs commitment from the whole organization, especially from top leadership. It has to be driven from the top.
Now, the name itself, Six Sigma, it sounds statistical. What does sigma actually mean here?
It is statistical. Sigma is a letter from the Greek alphabet used in statistics to represent standard deviation, which is a measure of variation.
Okay.
In this context, sigma essentially measures how much a process deviates from perfection or from the desired target.
Oh,
So a higher sigma number means less deviation, less variation, and therefore closer to perfection, fewer defects.
and the specific target for Six Sigma performance, what defect rate are we talking about?
The benchmark is incredibly high. It's defined as 3.4 defects per million opportunities, or DPMO.
Wow, 3.4 defects in a million.
It's exactly, which translates to 99.999966% accuracy or yield. It's an extremely high standard. The underlying logic is measure where you are now, find the causes of the defects, fix them, and drive that defect rate down towards that 3.4 DPMO goal.
The materials we looked at had a table showing the defect rates for different sigma levels, from 1 sigma up to 6 sigma. It's quite a jump between levels.
It really is dramatic. That table makes it clear how quickly the defect rate plummets as you improve your sigma level. You go from, hundreds of thousands of defects per million at low sigma levels down to just 3.4 at 6 sigma.
So even moving from, say, 3 sigma to 4 sigma is a huge improvement.
Absolutely huge. While achieving that perfect Six Sigma might be unrealistic or unnecessary for every single process, the benefits in terms of quality, cost reduction, customer satisfaction, profitability that come from moving up even 1 Sigma level are substantial.
Right. So if a company decides, okay, we want to implement Six Sigma, how do they go about it? Are there set methods?
Yes, there are two main methodologies that form the backbone of Six Sigma implementation, DMAIC and DMADV.
Okay, let's break those down. DMAIC.
DMAIC stands for Define, Measure, Analyze, Improve, and Control. DMAIC is the most common one. And it's a really robust data-driven method used specifically for improving existing business processes.
Improving existing processes. When would you typically use DMAIC?
You'd use DMAIC when you already have a process in place. Maybe it's underperforming or causing problems, and you want to make significant improvements. It's often part of a continuous improvement culture.
Okay.
It's also good when you need to tweak a single process rather than design something totally new, and when things like your competitors, customer needs, and technology are relatively stable.
The materials gave an example from banking. Can you walk us through how DMAIC might apply there?
Sure. Let's say a bank wants to improve customer satisfaction.
Okay.
In the define phase, they'd clearly define the problem, the project goals, and what the customer actually wants, maybe focusing on reducing wait times. Measure would involve collecting data on the current process. How long are customers waiting? What are the key metrics? Analyze is where they dig into that data to find the root causes of the long wait times. Is it staffing, inefficient procedures, technology issues?
Makes sense.
Improve is about developing, testing, and implementing solutions to address those root causes, maybe redesigning the queue system or implementing new software. And finally, control. This means putting measures in place to sustain the gains, monitoring wait times going forward, standardizing the new process, making sure it doesn't slip back, and if it's not hitting the goals, you might loop back to define.
Okay, that's clear. There was also a mention of a Derby Gray case study. Luggage bags.
Yeah, that was just another practical example.
Yeah.
A luggage company seeing too many sales returns.
Right.
They could use DMAA. Let's find the problem, high returns.
Mhm.
Measure the return rate and types of defects. Analyze why the bags are being returned, faulty zippers, poor stitching.
Yeah.
Improve the manufacturing or design process. Control the process to ensure returns stay low. It just shows the steps in a real-world context.
Got it. So that's DMAIC for improving existing stuff. What about the other one, DMADV?
Right, DMADV. That stands for define, measure, analyze, design, and verify. DMADV.
Design and verify, not improve and control.
Exactly. DMADV is different. It's used for creating new products or processes, or sometimes for a major redesign of an existing one, aiming for Six Sigma quality right from the start. The focus is heavily on designing quality in based on customer requirements.
So when would you choose DMADV over DMASC?
You'd go for DMADV when there's no existing process to improve, or maybe an existing one is so broken that tweaking it with DMAIC isn't enough. You need a fundamental redesign.
Okay.
It's also common for really strategic projects, or when you need to change multiple processes at once, or if the market, customers, or technology are changing rapidly, requiring a fresh approach.
Do they share any similarities, these two methodologies, despite the different goals?
Oh, yeah, definitely. They both stem from the same Six Sigma philosophy. Both rely heavily on data and that DPMO metric. Both use many of the same statistical tools and quality management techniques.
And the customer focus.
Absolutely central to both. Understanding and meeting customer needs is paramount in both DMAIC and DMADV. They're both systematic, just applied differently.
So boiling it down, DMADC fixes, DMADV creates.
That's a pretty good shorthand, yeah. DMAIC is more reactive, fixing problems in what you already have. DMADV is more proactive, designing quality from the beginning for something new or redesigned.
And maybe the payback time is different?
Generally, yes. You often see the financial benefits, the rupee benefits, as the source might say, a bit quicker with DMAIC projects because you're improving something already running. DMADV might have a longer lead time before the benefits are fully realized.
The materials gave some examples of problems suited for each. Can you give us a couple?
Sure. For DMADC, think about things like reducing the time it takes to process an invoice, cutting down errors in a customer database, making it faster to find information on an internal website, existing process improvements.
Okay. And for DMADV?
For DMADV, think bigger picture, new creation. Launching a totally new online banking service, creating a real-time inventory tracking system where none existed, designing a system to track sales leads from multiple different sources, building something new.
Right. That clarifies the difference well. Now, Six Sigma sounds powerful, but like anything, it must have its limitations or criticisms, right?
It does. No methodology is perfect for every situation.
What are some of the common ones mentioned?
Well, one criticism is its intense focus on quality and defect reduction might sometimes overshadow other important factors like, say, speed to market or radical innovation.
Okay. Tunnel vision, maybe?
Potentially, yeah. It can also be difficult to apply rigorously when the results are intangible or hard to measure. Precisely think creative processes or some HR functions.
Makes sense.
Implementing it properly requires a significant investment in training people, building that infrastructure of belts. That can be a barrier, especially for smaller companies. Can be. Some find it overly complex or bureaucratic for simpler tasks. And, not every single product or process needs that ultra-high 3.4 DPMO level of quality. Sometimes good enough is actually good enough.
Right. Is it applicable everywhere?
It tends to work best on specific types of processes, usually well-defined, repeatable ones. And finally, there's always the challenge of translating the theory and the stats into practical, everyday improvements on the shop floor or in the office. The real-world barriers.
Okay. But there's this idea of Lean Six Sigma that tries to combine things.
Exactly. Lean Six Sigma is seen by many as the best of both worlds. It integrates Lean's focus on speed, flow, and waste elimination with Six Sigma's focus on quality, variation reduction, and defect elimination.
So speed and quality.
That's the goal. By using them together, the idea is you get greater results than either one alone. Faster processes that are also high quality. It aims to help organizations, maximize profits, build better teams, cut costs, and keep customers happy. A powerful combination.
And the sources mention Wipro in India as a company that really embraced Six Sigma successfully.
Yeah, Wipro was an early and prominent adopter in India. They built a very mature Six Sigma program.
What were their results like?
They reported things like much higher rates of finishing projects on time compared to industry norms. For them, Six Sigma was key to hitting global quality standards, making their internal processes really solid and reliable, meeting customer expectations consistently, and just building a strong quality culture overall, backed up by a lot of training.
So wrapping this up then, it really seems like understanding both cellular manufacturing and Six Sigma gives organizations some very powerful tools for improvement.
Absolutely. They offer different lenses, different approaches, but both drive towards operational excellence. Cellular manufacturing focuses on streamlining that physical flow, cutting waste on the ground,
Right.
while Six Sigma brings that rigorous, data-driven discipline to root out defects and variation, boosting quality.
And even though they're distinct, they both really echo that core lean idea. Continuous improvement, always focusing on delivering value for the customer.
Exactly right. Different paths, maybe,
Yeah.
but heading towards the same fundamental goals of efficiency and quality.
So a final thought for you, our listeners, as you think about all this, how could these ideas streamlined flow from cellular manufacturing, data-driven defect reduction from Six Sigma apply beyond the factory? Think about your own work, maybe even personal projects. Where's the waste you could remove? Where are the opportunities to improve quality? Definitely something to chew on.
Food for thought, indeed.
Thanks for joining us on this deep dive.